Swayam Prabha. Digital India. Educated India.
So, today we will discuss something about fracture, the different kinds of fracture, under what conditions they occur. So, let us see a picture here. It is a very apt picture where a ship, these were called as Liberty ships, which were anchored in World War II in near Scandinavian countries, and then because of extreme cold, the otherwise ductile material became brittle, and then the ships just cracked into two pieces. I mean, it just split into two pieces. So, essentially the fracture can take place very spontaneously without any prior warning, or it can be an outcome of a large amount of plastic deformation or permanent change in shape, localization of strain, and subsequent fracture. So, the fracture can take place all of a sudden precipitously, or it can take place over certain amount of plastic strain. So, in fracture, the part necessarily breaks into two pieces. So, here I would distinguish between fracture and failure. We have been discussing failure earlier. Failure refers to a situation where the product or a part or piece of metal ceases to perform its designated function. So, if you have designed a part to perform a particular function, maybe a bolt, a nut to hold a certain amount of load, a hook, crane hook for supporting certain amount of load. Well, the inability of the hook to support that much amount of load would be treated as failure, but the hook can also fracture, meaning that the hook can split into two pieces under certain circumstances, and therefore break into two. So, the integrity of the structure can be maintained in spite of the structure failing to do its job. However, in case of fracture, the structure actually breaks into a number of pieces. So, this is a symptom of overload or overload beyond the capacity of the structure. Again, I would emphasize that every structure is designed for certain magnitude of overload. Let us say you design a structure like a ladder or whatever, you might design that product for a certain amount of load. A lift, for example, is designed for a certain amount of load, but then it does not mean that the lift will cease to work or it will break down if even few grams of load are added to the maximum capacity that is mentioned on the lift. So, the overload means any overload beyond the designed overload capacity. So, typically when we design something, we may provide about 20% of overload capacity. So, if the lift is designed for say 500 kilos, the lift will actually be able to take 600 kilos, right. The rated capacity is 500 kilos, the lift will actually take 600 kilos. Again, the idea here is that even if there is some overload, there should be no failure of the lift. So, here failure will refer to the lift being unable to lift the load up, and so it does not refer to any fracture as such, but its inability to lift the load or go up and down. So, fracture is a much more serious situation compared to just failure. Failure might happen even if the structure is intact, the integrity is preserved, but here in fracture the integrity is completely destroyed. So, the part breaks into two or more pieces, and it can happen if the overload is excessive in nature. For example, if you go on loading, let us say the overload capacity of the lift is up to 600 kilos, and then you keep on loading it beyond that, it is possible that the rope which lifts the cage up might snap, or it may start deforming, or finally might get its structural integrity might get compromised. So that is the reason why we need to study fracture, and it can be either a ductile fracture or a brittle fracture. A ductile fracture is something that does not take place all of a sudden. It gives you some indication earlier, that is there is some permanent elongation. Normally a structure is not supposed to elongate permanently, it is supposed to undergo only elastic deformation, meaning recoverable deformation. But then it is possible that because of overload the stress gets into a plastic zone or a permanent deformation zone. So in that regime there is permanent deformation of the rope or whatever you might be using to take the lift up, and then the cross section of the rope will continuously decrease in area, and so over a period of time it will deteriorate, and then and finally there will be failure resulting in the lift dropping from a certain height depending on where the failure took place. But then you have plenty of time to understand that the lift that the rope is elongating, because you will find that the lift is not going up as fast as it should, right. So or the lift is coming down much faster than what it should. So naturally the fracture is there is some prior indication before you can really anticipate that fracture. So in ductile fracture there is plastic deformation before the failure takes place. However, a brittle fracture like what you find in case of if you drop a cup or a glass bottle, it will immediately fracture into several pieces. So this is something where there is no plastic deformation, there is no permanent deformation. There is some elastic deformation as a result of the impact, but then if the elastic deformation is too much, it will result in a fracture. There is no room for any permanent deformation like plastic deformation. So brittle fracture is an event where prior to that there is complete integrity of the structure, beyond that there is no integrity of the structure at all. So there is absolutely no question of existence of a structure after the brittle fracture has taken place. So this transition is all of a sudden, it happens without a warning, and until this occurs the material deforms under elastic conditions only. Now no product or no material can be foolproof or flawless, right. So there are flaws in every material, there are flaws which arise during manufacture of that product or a component. Flaws can arise during the assembly, flaws can arise at any stage of manufacture and use. In fact, the user might also abuse the part or a component, and the flaws might arise as a result of that. But then flaws in the material will always promote fracture. So naturally you have to beware of these flaws. Some flaws could be internal flaws which are not visible. There are techniques to make them visible, but then some flaws could be on the surface which would be visible, and then they may give you prior warning about the prior damage that might have taken place on the surface. So for critical applications like the rope of the lift, supposing you have used the lift for say 10 years, 15 years, 20 years, there will be a schedule for replacing the rope after a certain number of years have passed. So after certain hours of use over 10-20 years, it is possible that the rope will develop a flaw. Not that the rope will fail overnight, but the flaw itself will endanger the lives of passengers in the lift. So, naturally for critical applications like a lift or critical applications like a nuclear reactor or a power plant where failure would mean a large scale disaster, any defect that comes into picture that gets generated either inside or on the surface necessitates the replacement of that part, overhauling of the entire power plant, replacing the worn out parts and so on. So, that is the reason why there is a schedule for replacement of components based on the experience that certain amount of damage could accumulate over a service period. And so, although the structurally the part is integral, structurally there is apparently no damage, still you would like to change the part and avoid any possibility of large scale disaster. So, for critical applications you do not let the fracture take place. The minute a defect arises in the part, you just replace the part. In fact, testing is often done for such critical parts where they monitor generation of defects and propagation of the defects, and therefore, when the defect tends to propagate, the life of the part is said to be over. So, people do not wait until the defect has propagated and led to a major flaw, which would in turn endanger fracture of that critical part. So, this is something which one has to be aware of, that flaws always exist in the material and they determine most often they determine the life of the component. In nuclear reactor type of applications, the flaws get generated internally during the service period. So, internal flaws get generated because of nuclear irradiation. So, after a certain number of days, even if the part is usable, apparently usable, it has to be replaced. I have already given you an example of the rope which is used for lifting a lift, which is of common use. Now, I will give another example of a chain which is made of several chain links and it is used for hoisting heavy loads. Again, all structural materials get tested to their full capacity when they try to lift heavy loads. So, the failed link indicated considerable deformation and necking prior to failure. So, here as I was explaining to you about the rope, because of overload, the cross sectional area continues to diminish because of plastic deformation, permanent deformation, and then the permanent deformation went to the extent that the failure took place by necking, meaning localized deformation, localized plastic deformation prior to failure. So, first reason, I mean if one tries to identify the reasons behind the failure, the description suggests that chain failed in a ductile manner by a simple tensile overload. So, the simple tensile overload led to plastic deformation. So, it went beyond the elastic deformation range. Being a structural material, being a structural element, it should not have been loaded beyond the elastic limit, but then it went into the regime of plastic deformation. Not only that, during plastic deformation we have seen that material work hardens and the depletion in cross sectional area is compensated by an increase in strength in the material, but then the overload was so high that even there the material continued to deform permanently in a plastic deformation regime. So, the cross section continued to get depleted over a period of time, and then that led to a neck formation in one of the chains, and you know that the chain is as strong as the weakest link. So, whenever a neck forms in one of the links, it is a perfect recipe for failure because that there is no further ductility that is left in the material. The failure will be very rapid. So, the tensile overload is something that should have been avoided, but then let us see the various possible causes rather than taking only one cause into account. The load exceeded the hoisting capacity of the chain, and therefore, the stress due to the load exceeded the yield strength of the chain, permitting failure. That is what I have just explained to you. So, that is quite an obvious conclusion, but this kind of overload failure can take place because of reasons which lie in the material itself. So, if you look at the load due to manufacturer specifications, right, if the chain was not intended for such use. So, manufacturer had used some material and that material did not permit certain amount of load to be carried and you use that. So, again it is a wrong application of the chain. So, if the application at the user's end is wrong, then the user is at fault. So, the question of failure arose because not because the chain was weak, but because it was misapplied by the user. But then user can't be always wrong, because once the manufacturer specifications have been adhered to by the user, in spite of that the chain material can fail. The reasons could be that the chain material was of wrong chemical composition, or it was improperly heat treated. I mean, you took the chemical composition correctly, you made the chains, you welded them together, but then the heat treatment, meaning heating the chain after all processes have been completed to get the right microstructure. Well, heat treatment is a process where you heat the material to a high temperature so as to get the right microstructure. Of course, merely heating will not do, you need to cool it down at a specific rate. So, depending on how fast you cool it down and the temperature from which you cool it down, you get different kinds of microstructure. So, now you are generating a particular microstructure to enable the chain to take a very heavy load, to take its rated load. So, if the microstructure that was required was not obtained properly, then you will find that the chain might not have the strength to withstand the load which was being handled. What it means is that, well, the chain did have the strength by and large, but then there were some weak spots left behind due to local heat treatment, meaning the heat treatment not having been uniform all over, and some local soft spots were left behind which were not capable of carrying that load, and due to which a rated load, even if the user had loaded the hoist to its rated load, still the chain broke. So, it is important that the material, the heat treatment of the material, the microstructure of the material has to be absolutely uniform everywhere in the entire chain, in every link of the chain for that matter. So, this includes the weldments, because you weld the chain links. So, different processes for welding are used, different consumables could be used. So, the welding process governs the microstructure, and its subsequent heat treatment will also influence the microstructure and thereby the strength of the link of the chain. So, this is another reason. Fourth reason is residual stresses are present in the chain. Now, many times during welding or during the course of manufacture, residual stresses might be present. So, these residual stresses are essentially unreleased elastic stresses. So, for example, I told you that during plastic deformation, the material undergoes work hardening, there is uniform deformation, but then if you unload the material, the elastic deformation is always recovered, elastic strains are always recovered. Now, during the course of manufacture of the chain, you subject it to permanent deformation, forming earlier the link which was formed was in the form of a straight bar, and then you bent the bar to form the link, and then you welded the two ends of the bar to form a chain link. So, in this entire process, at the end of the bending and welding, as the elastic stresses were not allowed to relax, the weld can be under continuous tension. So, that is what we call as residual stresses, because when you bend the chain into the round shape it was supposed to get, then if you leave the chain as it is, you will have a gap generated between its two ends. So, you have a chain like this, you have brought these two ends together, and then after you release the load, there is a gap created between the two ends. So, what you do is you press this together and then you weld it. So, you apply weld here, or you might also use solid state welding processes. But then what has happened is you have welded it, and once the weld has cooled down, then this chain will try to release its elastic stresses. So, these two ends will tend to move apart, but then that will not being allowed. Why is it not being allowed? Because the weld is holding it together. But the necessity or the tendency of these two ends to go apart will result in continuous tension being introduced into the weld which you have made. So, that is what we call as residual stresses. So, residual stresses are the stresses which are applied to the chain link even before any load has been put on it. So, let us say the chain is rated for 1000 kilonewtons, and then your residual stresses are to the extent of 200 kilonewtons, right. The residual stresses are to the extent of just 200 kilonewtons. Then what happens? You know that the chain is rated for 1000 kilonewtons, but already there is an internal load due to elastic stresses to the extent of 200 kilonewtons. So, the minute you will go beyond 800 kilonewtons, the chain will snap. Yet another factor would be the factor of safety in designing the chain. For example, if a chain rated for 1000 kilonewtons is manufactured to take only 1000 kilonewtons, it is not acceptable. That is because some overload capacity, as I was mentioning to you, at least 20 to 30% overload capacity has to be there, because in use it is not practical to use the chain or to restrict the use of chain to its maximum rated capacity. Sometimes overload is always possible. So, supposing there is small overload, the chain should be able to take it, although the user has to be careful in not overloading it significantly. So, what I mean is that the factor of safety which should have been taken while designing the chain was not adequate, due to which the initial cross section itself was not adequate to take the entire load. Now, this is particularly important because presence of residual stresses is an inevitable part of a manufacturing process, because you might induce residual stresses. The chain, the links, every link in the chain will have certain amount of residual stress present in it, and therefore, unless you take a sufficiently large factor of safety in design, you will not be able to address the issue of residual stresses, because then the capacity of the chain gets reduced by that much. So, if you want to enhance that or if you want to maintain the capacity, the rated capacity of the chain, and not get bogged down by the residual stresses present, then you need to have a sufficiently large factor of safety in design, so that not only overloading by the user, but also apparent overloading due to presence of residual stresses are taken care of. So, these two factors are very important, and a generous factor of safety has to be used for design of the chain. So, this is another reason why overload failure can take place. So, it is not just one reason, but there are many underlying reasons which can be traced back to the design and the manufacturing process, which are upstream of the use, upstream of the application that are responsible for the ductile failure of the chain. So, how do you distinguish between a ductile failure and a brittle failure from the looks of it? Now, if you look at the typical failure in a ductile material, it is kind of cup and cone fracture. So, at the center is the so called fibrous zone, and this fibrous zone under a electron microscope looks something like this. That is because as you go on deforming, I told you that the absolutely clean material is a hypothetical concept. So, you have some inclusions, you have particles, intermetallics of different hardness, and now as you go on deforming the material, there is nucleation of voids in the material, and these voids become bigger and bigger with increasing strain, because now the voids have ligaments which are present in between the two voids. In fact, the shape and size of the void gets defined by the ligament. Initially, the ligaments would be very thick, so voids would be in the form of very micro sized voids. But then as the deformation progresses, the plastic deformation progresses, although you might find that deformation is uniform outside, there is absolutely no non-uniformity in deformation. Internally, you will find that these ligaments are deforming and getting thinner and thinner. So, as this happens, these voids continue to grow in size, and when these voids continue to grow in size, the ligaments can snap at between two voids and the two voids can coalesce. So, which means that two voids can get integrated into a single bigger void. So, now the load carrying capacity is getting depleted on a microscopic scale. On a macroscopic scale, you will find that the load carrying capacity is good, it is adequate because material is work hardening. So, these are the ligaments which would be work hardening during deformation, but then as they grow thinner and thinner, they would fail, and because of the failure of the ligaments, you will have coalescence of voids, and voids per se do not have any load carrying capability. So, the cross section of the material that carries load will continue to get depleted because of the growth of these voids, and then there will be a point at which the cross section just does not have enough strength to carry the load, in which case there will be shearing at the periphery, shear failure at the periphery of this, and therefore, you will have what is called as the shear lip. So, now you have two components, you have a fibrous zone which is the center and the shear lip which is at the periphery, and this is typical of a ductile fracture. So, this is a cup and cone fracture which has formed because of a neck formation. So, necking is essentially localization of strain here. So, you see that localized thinning of the cross section has taken place. Well, in this case that thinning has taken place to the extent that the material has reduced to a point and then the failure has taken place. So, these are extremely ductile materials like gold, for example, where failure would take place by reducing the cross section to a point. A point has no area as such, the area of a point is 0. So, the material continues to deform, material continues to deform until the failure has taken place at a point. Whereas, here it is also a ductile fracture, but then it has not gone up to a point. That is because the internal voids have grown, and these internal voids have resulted in depletion of the cross section, the actual cross section which carries a load, and subsequent shear lip formation over here. So, that is why there is a reduction in area which is substantial compared to what you have here, but then it is not as large as what you have here. So, this is an extreme case of ductility, extremely high level of ductility as in case of gold, and many of the face centered cubic materials have exhibit very high level of ductility, and they exhibit extremely large reduction in cross sectional area at the time of fracture. So, ductile fracture will have an extremely large reduction in cross sectional area together with the fibrous cup and cone type of fracture which is typical of steel and many ductile materials. Brittle fracture on the other hand has it's plain and it's shining. So, it is basically a intergranular fracture. A brittle fracture occurs, the failure occurs between two grains, whereas in case of ductile fracture it is transgranular fracture. That is because the deformation takes place inside the grains, the ductility of the material is due to deformation in the grains. So, I am presuming that it is a room temperature deformation, or the deformation is taking place in at the temperature regime which is below the so called equicohesive temperature. So, here the grain boundary is stronger than the interior of the grain. So, the ductile deformation takes place in the interior of the grain, and then after substantial deformation these voids grow, coalesce, and then there is a cup and cone type of fracture taking place in the material after a substantial reduction in the cross sectional area. Compared with the brittle fracture, it is not transgranular, it is intergranular fracture. So, it is a intergranular fracture, meaning the crack propagates between two grains and there is no evidence of any kind of ductility. So, there is no reduction in cross section as such. So, there is no plasticity which is exhibited by the material, and so the appearance of such fracture features is in the form of shining facets of grain boundary. So, since it is a intergranular fracture, you see that the grains, different facets of the grains are shining, meaning they reflect light very well. So that is the reason why the brittle fracture looks very bright, whereas the ductile fracture looks very dull. So the reflectivity of a brittle fracture is because of the intercrystalline fracture or intercrystalline nature of the fracture. Now fracture can occur because of let us say longitudinal or tensile overload, and typically you see the dimples like this. These are called as dimples on the fractograph, and here you see these are shear dimples, which means that which arise because of shear loading. So when the loading is in shear and there is substantial ductility under shear loading, you will see the voids growing in a particular direction. So voids will grow, but then the morphology of these voids is different, the shape of the void is different as opposed to tensile loading as shown over here. So this is a brief glimpse of cup and cone fracture here. So you have this as a male portion of the cup and cone fracture, and this is the female portion of the cup and cone fractures. Now this is not manufactured this way, it gets generated during the course of fracture process, and this happens in different stages as depicted over here. So what happens is there is an initial decrease in the cross sectional area. So there is a imminent necking as it is called. So this is shown in exaggerated manner. So what you see here is a diffuse neck. What it means is that it is not easily visible, but then there is a decrease in the cross sectional area which is shown in an extremely exaggerated manner over here, and so this is the imminent localization of strain. So the strain in the material tends to get progressively localized in this region, which is a relatively thinner region, meaning the region which has got reduced in cross section faster compared to the remaining areas in the neighborhood. Now because of high strains, voids tend to get nucleated at the center. So the void get nucleated in the central portion, because that is the portion that is strained the most, and then you have depletion of load carrying capacity, depletion of area, load carrying area. Again therefore the concentration of strain becomes more pronounced, because now this is the weakest, mechanically weakest area due to the depletion in cross section. The voids have been generated, there are plenty of voids which are distributed over the entire cross section, and due to that the cross section continuously gets depleted with strain, and therefore there is progressive concentration of strain in this particular region. Now these voids coalesce as I just mentioned to you, and they form an internal crack. So there is a big crack inside. Of course there will be evidences of high level of ductility, because before the crack gets formed the voids grow in and then they coalesce. So there is an evidence of growth of voids to a larger sizes and then coalescence, and then after that when there is a large void and then the material has lost its load carrying capacity completely, it snaps into two by shear. So this is a shear lip. So there is a shear fracture over here at these two ends, and then there is a fibrous fracture zone at the center indicating very high levels of ductility. Brittle fracture in contrast is an intergranular fracture. So you have the fracture running through the grain boundary. So the path of fracture is through the grain boundaries, and so it all depends on the path taken by the crack to propagate. So it is not that the crack will propagate along just one path, as you see that this is the origin of fracture for example, and then the crack has propagated in different directions as you see over here. So it is not that there is only one path for propagation of a crack, it can propagate along many directions as you see over here. So the crack propagates radially outwards. So it creates a kind of pattern of paths of crack propagation, and finally the failure takes place. So, now this is the intergranular failure taking place without any prior warning, without any plastic deformation taking place. So, that is why it is a brittle fracture. So, this brittle fracture is intergranular, it occurs all of a sudden, and the piece snaps into two parts. Well, we do take often some advantage of this brittle nature of fracture. For example, if you want to break glass into two pieces, you just make an artificially a crack, meaning you introduce a scratch using a diamond tool, and this scratch acts as a crack which will propagate as you bend the glass plate. So, if you want to break the glass plate into two pieces at a particular location, as it is shown over here, then you make just a scratch, and that is enough, because that scratch acts as a notch or a crack, and then it propagates very rapidly without any plastic deformation. So, that is what is seen over here, and you will find that there is brittle fracture all over, because you will find a shining fracture surface characteristic of these the facets of these grains being exposed to the light. So, that is how the light gets reflected from these fracture facets. So, this could be metal, this could be glass or anything else, basically brittle material where there is a intergranular fracture taking place. So, in brittle fracture, the kind of paths which are taken by the crack to propagate and result in complete separation between two parts is called as river patterns. So, these are kind of river patterns because the different paths taken by the crack resemble the river pattern that we see in nature. So, this tells you helps you to find where the crack originated. So, if you find the river pattern, you try to go upstream. So, you go upstream along every river segment, then you will finally converge onto the region where the crack originated, because the crack always goes away from its point of origin. So, the crack once formed will dissipate energy, the so called surface energy, by creating more surfaces. So, the creation of more surfaces will result from the crack branching out into different directions and creating a river pattern like that. Yeah. In contrast, you see the transgranular fracture over here. So, you have fracture running through many grains. So, you have a number of grains through which the fracture is running, and before separation there is substantial amount of ductility that is found over here. Well, you can have a fracture taking place under shear, and like in case of shear lip which I mentioned to you earlier, where the fracture takes place over an extremely small amount of strain, in which case you will see these shear facets, okay, without any dimples or without any evidence of voids having grown and the material having failed by void coalescence and failure. So, when you have the shear lip type of formation, then although the fracture is transgranular, it will still not have sufficient ductile features or features indicating significant amount of ductility. But on the other hand, you look here, so these features are refer to dimples which were generated as the material behaved in a ductile manner. So, we must remember that no material is perfect or flawless. Discontinuities, inclusions, geometric flaws like notches, machine marks. So, when you do machining, you might leave some machine marks behind. So, many times you do a facing operation, even during facing operation you have those marks of the facing tool left behind. So, these are something which are part and parcel of the manufacturing process itself. Atomic scale defects do not count as flaws. So, what is a flaw? flaw is something of a macroscopic nature, well beyond the atomic scale. So, the flaws are of much higher scale. We have studied crystallographic defects like dislocations or point defects like vacancies or interstitials and so on, but we are not talking about those defects. We are talking about flaws which are macroscopic in nature, which are left behind or which are generated because of impurities in the material, intermetallics getting formed by impurities combining together, and which generally deplete significantly the load carrying capacity of a cross section. So, the flaws grow in time under stress, and especially the tensile stress, because in compressive stress the flaws do not grow and the interface between flaws and the material gets kind of compressed together. So, there is no room for any breaking up, or there is no room for any delamination of interfaces. But if you have any delamination, it does require a tensile stress to be acting on it. So, naturally you will find that flaws grow with time under stress, especially the tensile stress. Flaws join up to cause failure. So, I talked to you about void coalescence. So, you have these again voids which essentially are flaws of a macroscopic nature, and these flaws will join together to create a crack. So, sometimes these once the crack is generated, it can propagate precipitously leading to a sudden fracture. Mechanical behavior of materials in the presence of flaws is fracture mechanics. So, now once you accept the fact that no material is foolproof, no material is absolutely clean, then you need to make use of the material very cautiously. So, what it means is that you have to make sure that the flaw does not generate to a crack that will propagate. So, even if the flaw is in form of a crack, one has to make sure that the crack does not propagate during the course of use. Now, different techniques which are used for detecting these flaws have limitations, like the smallest flaw that can be detected by technique A and the smallest flaw detected by technique B could differ. So, you cannot go beyond a certain limit when it comes to detecting flaws. So, essentially you have still some flaws left behind, and these flaws will result in gradual development of cracks or propagation of these flaws, enhancement of these flaws over the service period, leading to a final failure. So, final failure in the form of fracture would take place if the flaws were to grow over period of time of service, if they were to coalesce and then they were to form a crack and finally snap into two. So, the life of the component would be the time duration that is needed for the flaws to grow. So, we do not wait until the flaws have come together and have formed a crack to finally cause separation, but we would say that once the percentage of flaws reaches a certain value. So, once the flaws have grown to a certain percentage, we scrap the component, we discard the component. So, how do these flaws propagate? So, this is how they do. So, this is a surface flaw, the depth of which is A, and then there is a small radius of curvature for every flaw. So, it could be a notch, it could be a crack, it could be something else, it could be a scratch. There could be an internal flaw in case of castings, for example, you have blowholes, pinholes and things like that. So, there are internal discontinuities which are present in the material due to for various reasons, and so you have an internal flaw, and then each internal flaw has got its own radius as well. So, now if you take the stress, you have a load divided by the cross sectional area, but now if you take this entire cross sectional area, that is not really the load acting on the material, it is actually the average load acting on the material. So, what has happened here is this portion is not carrying any load at all. So, all the load is being carried by the healthy portion. So, now as you approach, so at the ends you will find that there is some average load being carried, but then as you move closer to this, you will find that this stress is being the stress that is experienced by the material very close to the flaw is extremely high. So, compared to the stress over here, as you move towards the flaw here, the stress can be found to rise extremely rapidly, and sharper is the flaw, meaning if the radius of curvature of the flaw is extremely small, it is a very sharp flaw, then you will find that the stress intensity rises extremely rapidly. So, this intensification of the stress takes place extremely rapidly. So, this is a stress distribution in a specimen with a crack or some defect or a discontinuity, something like that. So, everything is being shown exaggerated. So, for example, here the opening is usually not so big, whereas and here also you do not have such a big flaw, but then just for our understanding, just for sake of understanding the concept, it has been drawn that way. So, we need a factor like stress concentration factor like Kt, which will measure the intensity, the intensification of stress at a flaw. So, what you see is that Kt is essentially the mean stress by the average or maximum stress experienced by the material divided by the average stress or the mean stress that is experienced all over. So, this is the average value of the stress, which is supposed to be experienced based on the load divided by the cross sectional area, and then as you approach the flaw, it gets intensified depending on the size of the flaw A and its radius of curvature T. So, larger is the flaw, larger is the size of the flaw, and smaller is the radius, more deadly it becomes, because the stress gets concentrated very rapidly, and if the material is ductile, then it will undergo substantial deformation in the vicinity of this particular sharp radius in the vicinity of the flaw. So, the stress gets intensified to a very significant degree. So, 2 sigma naught into A by rho root of that is the stress intensity factor. So, the stress gets intensified to the extent of 2 into A by rho under root, right. Okay. Now, what happens in brittle fracture? In case of brittle fracture, the plastic zone does not deform at all, plastic zone does not get formed at all. So, there is no question of plastic deformation taking place. Normally what happens is, if the plastic deformation were to take place at this zone because of intensification of the stress, then the crack tip gets blunted, the energy. So, certain amount of energy is required to generate a new surface, but then that energy is absorbed by the plastic deformation. So, the plastic deformation absorbs certain amount of energy that might be available, and so there is no propagation of the crack. So, there is so called blunting of the crack, because the radius of curvature of this particular discontinuity increases as the plastic deformation increases. So, naturally the stress concentration comes down, and therefore, the crack propagation gets arrested if there is a plastic zone formation ahead of this. So, blunting of the crack or lowering of this value of Kt would mean that the sigma m has reduced, the stress intensity has got reduced, because the rho t has increased significantly. So, as rho t increases, then your sigma m decreases, and when sigma m decreases, this Kt, which is stress concentration factor, that also decreases. So, with lesser stress concentration, there is better distribution of stress all over, and therefore, the crack does not propagate. So, the crack propagation gets arrested, and this kind of thing is perfectly acceptable. So, you can still use the component even in the presence of the crack, because now the crack is now no longer propagating. So, if you take a brittle fracture in contrast, you will find that the crack tip over here, as it is called, has got a certain radius, a sharp radius actually, and then the stress intensity results in very rapid propagation of this crack because there is no plastic deformation. So, the energy available, so energy of fracture is essentially the surface energy that is available for creating new surfaces. So, this is a very important concept. So, this is a so called Griffith crack, it is a crack or a so called Griffith flaw, and it has got length A and radius R, as has already been explained earlier. So, when the crack radius is small, crack tip radius is small, sharp radius, or when crack is long, the ratio of sigma actual upon sigma is extremely high. Sigma actual at the crack tip is far greater than sigma y, then the crack will grow and it will cause failure despite a small nominal stress. So, your stress concentration factor, stress intensity factor will be extremely high in this case, because now the crack is going to propagate very rapidly through the material. It could be intergranular or transgranular, but the basic thing is that it will propagate very rapidly, and the stress concentration itself would make sure that in spite of having a low average stress, the fracture takes place and the crack propagates. If the material is ductile, yielding a crack tip, okay, yielding at the crack tip causes plastic deformation. I have just explained this to you, and so so you can therefore calculate a stress, so called critical stress, so that the strain energy that is stored in the by plastic deformation and the surface energy that is available are compared, and when they become equal, then you have the value of sigma critical, beyond which the surface energy available will be far greater than the strain than the energy that can be absorbed by the plastic zone as strain energy. So, the energy that is available, surface energy that is available is far in excess of what can be absorbed by the ductile nature of the material, and then the crack will therefore start propagating and finally fail. So, sigma critical is the critical stress for a material having crack of length A. Okay, the material has a crack of length A, meaning from the surface, as you see, there is a crack of length A, and the critical stress for that is given by this expression, where gamma is the surface energy per unit area. So, this is a very important concept, and once it is based on this surface energy per unit area, you get the value of sigma critical. So, simultaneously you can also find out for a given stress what is the critical crack length. So, you know that a component is to be loaded to a certain stress is going to be generated in the component, and you would like to know, or you would like to specify the maximum flaw size that can be tolerated without any fracture. So, you allow the manufacturer, you allow the designer to work with a material with a certain size of the flaw, so that even if the material is subjected to load, the rated load, the crack will not propagate. So, this is a very important thing. As long as the crack does not propagate, as long as the flaw does not get enlarged in size, does not propagate, you can still use the component or use the material. Okay. So, in terms of stress intensity factor, the normal applied stress at which the crack would propagate. So, sigma critical is k upon f root of pi a, and where f is a constant factor, okay, so which will be defined as we go along. So, if you look at the size of the flaw, a small flaw causes a significantly lower load carrying capacity at imminent propagation of the crack. So, if the A is relatively small, okay, then sigma is relatively more, okay. Whereas A is large, then sigma will also be large. But then a small flaw meaning small sized flaw with a sharp radius, okay. The radius is very important. So, it will significantly reduce the load carrying capacity because it will intensify the stress. So, the stress intensity factor K is very important here. Flaws are especially important in the presence of tensile processes. So, typically the size of cracks which are detectable by different techniques, I have been mentioning this to you, that different techniques are capable of detecting different kinds of different sizes of cracks. So, X-ray radiography can detect 0.02 inches crack, meaning 0.02 into 25.4 will give you the crack size in millimeters. So, maybe a half a millimeter crack will be detectable using X-ray radiography. Whereas gamma ray radiography will be able to detect a much smaller crack, right. So, 0.008, so 8 micro inches is the size of the crack that can be detected, okay. So, this is essentially 0.2 millimeters. So, instead of 0.5 millimeter large crack, so 0.2 millimeter crack will not be detectable using X-ray radiography, but gamma ray radiography is capable of detecting 0.2 long crack, okay, or size of the crack is 0.2 millimeters. Similarly, ultrasonic inspection goes further down, 0.005, okay. So, essentially it is 5 micro inches, instead of 8 micro inches it is 5 micro inches. So, essentially it will go to 0.125 okay, millimeters as the size of the crack. So, as you go from X-ray radiography to ultrasonic inspection, then you have the different sizes of crack which are detectable and minimum thickness that you can possibly go up to. So, minimum thickness is 0.19 inches or so 0.2 inches roughly, and with X-rays you can have minimum thickness of about 0.37 inches. So, 1/3 of that, essentially about 1 millimeter or thereabouts should be the minimum thickness. So, I have been telling you that microstructural features affect fracture, and we generally generate microstructures so that these features tend to arrest fracture. So, in the next class we will see in greater detail what are the microstructural features which promote fracture and what is needed to generate features which will prevent fracture. So, with this we will conclude our lecture here. Thank you.